I will join the meeting with my phone for June.
Good afternoon. We are Group 5 and we will be presenting on IoT-based predictive maintenance alarm system in SMT assembly line. Next. This is the team split. Jaije is responsible for hardware and embedded software design. So he did hardware selection and design embedded software based on the ESP IDF. Mincher Zhang, is in charge of communication with AWS. I designed the implement MQTT protocols. And lastly, Ashwin, he did cloud integration and machine learning. He did design of cloud architecture and deployed the machine learning. Next. Here is an overview of our presentation. I'll walk you through from the introduction to the conclusion. Our project aims to implement a predictive maintenance alarm system in our SMT line to select the data from this factory. We adapted three sensors that is collecting the parameters such as temperature, humidity, acceleration, and gas levels. And then before this data will be analyzed and collected and analyzed on AWS. We adapted the machine learning and abnormal situation would happen. It will send the notification or alert to the users. Next. To do this, we need to, for doing that, this is our three key requirements. It can enhance our safety and it can predict our maintenance. And by doing that, it can raise the energy efficiency. To do this, we need to monitor our machine running condition, and sensor data need to be uploaded to the cloud, and data analysis is on the cloud. So we can do abnormal prediction and sending alert or notification. We set our IoT level as 6. Next. We used multiple end node. We used three sensor nodes. Each board is connected to the AWS wirelessly, and data is stored and analyzed on the AWS. Next.
Hi, I'm Jesse. I'm responsible
Responsible for our hardware design of our project. And this slide shows our hardware setup. We can notice that the back tiny board with the blue gas sensor and the purple board in the middle is the temperature and humidity sensor, and the purple bar on the right is the accelerometer. And we had a buzzer placed the role as an actuator for indicating the emergency happened. And we are using the MPU 6500 as our accelerometer and AGS10 for our gas sensor. And we are using AHT20 for temperature and humidity sensing. The reason why we choose the Expressive ESP32 as our main processor is that it integrates 520 kilobytes SRAM, which is really sufficient for our IoT application. More importantly, it integrates the 2.5 gigs Wi-Fi and Bluetooth baseband and transceiver, which is a very valuable characteristic because it is integrated and we can purchase that in a relatively low price. And our design of our hardware system can be simplified. We are using the HHT cost, amenity, accuracy, and the reason why we are choosing MPU6500 as our accelerometer is that it has a wide range of acceleration full scale and with very high accuracy. The most important thing is that its refresh rate goes up to 1 kilohertz, and in this application, we achieved 700 hertz to capture our vibration data. And we are using AGS-10 gas sensor to detect flammable gas and TVOG data, and it is utilizing the I2C interface. And this is our test environment. The device on the test is actually a test cloud speaker. It can generate mechanical vibration for machinery equipment simulation. And we attach our accelerometer board to the diagram with an extension DuPont to minimize our inertia. Then we are trying to use a software signal generator to produce a certain frequency tone, which can represent the normal operation of our machinery. And then the ESP32 will capture the data produced from the accelerometer and pass them to our computer. Then we are using the MATLAB to add a low-pass filter to the raw data and do some DSP works, like doing the fast Fourier transform to extract the vibration spectrum in 3 dimensions, so we can capture the characteristic of the vibration signals. And first of all, the environmental sensors can be read out through the serial port. We can directly get the readings of our sensor status from the console. First, we can see that the humidity and temperature applied from the AHT20 sensor is 555 and 25 respectively, and we can read out the TVOG reading is 70% per billion. And what's more, the program also extracts the accelerometer's peak frequency, which is located at 49 hertz. And I will show a simple demonstration for our to prove our sensor they are running in good conditions. And now I'm going to start the online tone generator to generate a certain frequency of vibration. Here's the frequency generator, and now I can play the frequency tone through my speaker. And then when we can start the serial studio, which can visualize our raw acceleration data in 3 axes. You can see that the acceleration data is transmitted through the stereo studio, and it is visualizing the vibration magnitude and according to the samples we get. And then we are going to do some digital signal processing stuff through MATLAB in real time. Then we will start our MATLAB. Just wait a second. Starting. Okay, here's the script I'm writing, which can capture the data transmitted from the ESP, and it will apply a low-pass filter and a hand window, and then it will do the 1022 points FFT and extracts the frequency characteristic of the vibration signal. Let's run this program. We can see that the data has been transmitted to the MATLAB, and the spectrum diagram can be displayed, and we can observe that there's a peak at 60 Hertz, around 6 Hertz, in the dimensional spectrum, which can match the signal we set here. And when we change the frequency like to 80 or to 40, we can observe the peak has changed, moved to 40 Hertz accordingly. So which demonstrates that our accelerometer can work and the FFT ESP algorithm can work properly. Then I have implemented the FFT algorithm on the ESP32 natively to extract the frequency specification in real time and just upload them through MQTT protocol to our cloud. So now let me download the final version of our group project. Okay, I will close the C report. I'm downloading the final firmware of our ESP32 and demonstrates the whole running of our system. During this time, I will introduce what the embedded program do on our ESP32. First of all, the ESP32 will acquire 1024 points of acceleration data and store them in the flash. Then the FFT ESP module will do the calculations. Okay, it seems that it's working out. Yeah, and our system is initializing. It will try to connect to the Wi-Fi access point we set, and it is getting the real time from the RSTP server, and then it will start the capturing. Yes, we can turn on the signal generator now. Now the signal generator providing 60-40 Hertz frequency, and we can see from the console that, I will turn on my camera. Oh, can you see my camera? Yeah, now the speaker is now playing 40 Hertz audio, and the vibration sensor, the acceleration sensor, will capture the acceleration data, and we can show that on our console. The peak frequency is that it's 36 Hertz, which is really close to our set 40 Hertz. And we can see the readout magnitude of the peak frequency is the 10.5 dB. And all of our environmental data will be captured and packed and displayed here. And also we can show that our MQTT function is working, and it will send the packed information and publish them in our designated public topic. Yeah. And here's the structure of our hardware node program. It utilized 3 sensor drivers and a DSP core. Then it would pack and organize, do the data pre-processing with the FFT algorithm, and finally it would formatting a JSON string through the MQTT core and publish them to the topic.
On top of that, for the communication layer, this is our communication diagram. We used AWS as MQTT broker. Next. Our proposed system utilized 3 ESP32 IoT boards with the 3 sensors that collecting the data. This ESP32 board will continuously monitor the environmental condition in SMT assembly line, and then it uploads publish their data to the AWS named industrial/US East 2/ESP000. And then MQTT subscriber will collect all the published data, ensure that environment matches the set environmental level. And if the discrepancy are significant, it will send an alert or notification to users. Next. This is a demo video that's showing all of our sensor data is collected one AWS endpoint. And then the data is written in JSON format. Okay. Next.
Okay, I will stop my screen sharing, and then you can share your screen.
Yeah. My part of the project workflow comes under the cloud integration and the signal processing for the sensor data that we posted through Mosquito Broker. And my specialization comes for designing the machine learning model. We effectively understand the signal patterns and come up with a pipeline to send an alert to the user by predicting the abnormal cases. So here you could see the overall workflow of how the cloud architecture has been developed to make use of the sensors connected to the network and extract the valuable features for uh, inputting my machine learning model for the prediction. So here we are connecting all those sensors to the AWS Connect IoT core, and I'm later saving those information in the database. And from there, I'm querying the stored information through services like Grafana, where I'm developing the dashboard for the user and have another parallel workflow or the pipeline, I could say, where I'm having a machine learning pipeline for training and also for testing the data. So my program will have access to the database information and do the prediction later on, and thereby sending an alert if there is abnormal situations happening. In order to give the overlook on the sensor information that we are taking, so we have gas sensor information, accelerometers, and a few other environmental sensors like humidity sensor, gas resistance, indoor air quality sensors. So all those informations collectively help us to understand the machine condition. So we could able to predict uh, the machine state, like whether it is in normal working condition or it is in breakdown or about to get breakdown. So we could send an alarm to the user. So here I've just explained the overall sensor information data that we are utilizing. In just a recap again, but the catch is we have utilized velocity root mean square and displacement root mean square instead of acceleration data and gyroscope data because there are few supporting informations defined by ISO for detecting the vibrations. So just to give you an outlook, like these two are the vital informations required for processing these signals, so we could do effective predictions. Okay, so this in this slide, I'm explaining this would give you overall outlook, like why did we use random cut forest for training the machine learning model, and why it is best for use with our project proposal. So the first advantage is it like it's a unsupervised learning model, so we don't need to label all those sensor data to justify, okay, these are the sensor data that gives are responsible for the normal working condition of the machine, and other set of informations are the responsible for abnormal cases. So it's hard to label everything for each and every cases, and we have high volume informations coming up from each machine. So just to break down things, this algorithm is effectively trained on the normal working conditions. So whenever the machine learning model sees the not trained informations that are those faulty signals or the abnormal working cases, the machine learning model would effectively know, okay, these are not belong to normal working conditions. So thereby helping to easily to navigate the program to find the prediction. And why this algorithm? Since it's easy, we don't need to label things, and it's an unsupervised learning. It's more effective for time series predictions. And as like with other machine learning models, this pipeline is exactly same, but it's slightly different because the training is absolutely done on the good set of data, that is normal working conditions of the machine. So here I've just displayed the input data sets, that is the vibration, RMS, and the true ground truth information about the vibration and the normal working signals that is being recorded. So the entire time frame of this signal is around 10 seconds, And the purple ones are the normal working cases. It doesn't have any high frequency components attached, and remaining components are the faulty signals. So they have high frequency components involved. So the we could understand, okay, these are the vibrations of the machine. And so the velocity RMS is okay. It's been extracted by integrating the acceleration data. So since the normal signal that we are getting from normal operations have a lot of low frequency components, so when it has been integrated, so we are having the high peaks for the normal, but not to the other faulty signals. Since it doesn't have the low frequency components, it has the high frequency components. When it has been integrated, it doesn't show up in the velocity information. And I'm just showing you tabular information that I got extracted using the features for training my machine learning. The first one is the data that I use for training. So it shows all those velocity, displacement, RMS, temperature, humidity. These are the nominal working conditions. So it doesn't have any abrupt changes in the environmental sensor information or with the displacement and velocity stuff. But check on the prediction stuff that we have used to test the data sets. So the in the cases where we have anomaly false, so are the cases we have detected it is not alarming case. The other cases, the prediction where it is -1, those cases are the alarming cases. So this model is showing the outcome is more effective in predicting the abnormal cases. So it is the output from the machine learning model. So we have evaluated the model. So it is one among the performance curves to evaluate the machine learning model, since it is a time series information. So we are calculating the area under curve for the rolling statistic parameters. So I'm just skipping things, and it is the outcome of our performance of our machine learning model. The core is that our model is able to predict the alarming cases 88% times, so it is more effective. Here, it is this gives you the overall Amazon services involved in creating the network architecture. So we have the sensors attached, and every sensors are communicating to the IoT core. So it is the broker. So it is taking in the mosquito information from the sensors and the IoT core, which is handled by the AWS for extracting all those sensor information such a way it could be read by the database component of the infrastructure. So we have time stream. So we have among the other database services, it is used for time series information. That's why time stream. And from there, I'm splitting the workflow into two categories, two classes. The first class is for the demonstration, this dashboard purpose. So the Amazon Grafana service is for designing the dashboard for the system, and the thing is for machine learning pipeline. And so where we have two processes coming up. The first process is with training the component, and the other process is with the testing, like the actual deployment of the code. So the AWS Glue, Amazon SageMaker, Amazon SageMaker model, just to summarize. So these are the services involved in helping the model get trained on the normal information. So the user like me would have taken those information, like queried the tabular information from the time stream and trained the machine learning model, and I would have got the trained model. And later on, once it has been fully trained with the performance requirements, I'm having a service called Lambda. It is like a small micro um, service. It works independently without headless, so it doesn't need any top level programs or the operating system to run those programs. So it has been shared among the compute that we have for the AWS. So it runs at the background indefinitely. It will be hosting the machine learning algorithm with the training coming from the SageMaker. So it will also taking the information from time stream, the live real-time data. So those information along with the trained machine learning model will able to help in understanding the prediction and understanding the abnormal cases. Once this microservice finds out the setup, these are these combinations that are coming from the time stream responsible for the faulty signals. It would send the Amazon SNS, the simple notification system service. That service will handle email protocol for sending an email to the user. So that's the overall process involved in the cloud infrastructure. And before going on with the demo, I just want to know, I just want to explain on the signal processing involved for the machine learning. So, as I said, this is the time series information that I got for 10 seconds, actual true ground truth information for vibration with fault and without fault, normal working conditions. I'm using this information for training, inputting to my program for finding out velocity and displacement RMS. So the pulp of this is to understand this table. See, the normal working cases has velocity RMS higher relative to the faulty ones. So, and for these displacement RMS, it's exactly the same case. Like the normal ones has more value than the faulty ones. So that's how it's able to enabling the software to understand, okay, the velocity RMS and displacement RMS are the key components in understanding faulty signals with the normal conventional good working conditions. Okay. And for the data set itself, okay, this this is the output of the machine learning model, the ML output. So here we have velocity, displacement, RMS, and other environmental sensor information. The machine learning model is able to accurately predict whether these are the set of combinations responsible for the faulty information, say the one, and sorry, the faulty informations are labeled as -1, and the normal good conditions are labeled as 1. So our machine learning model is able to detect the faulty ones and abnormal ones and the normal ones. And for the machine learning part, so as usual, so I've created a pipeline for the machine learning random cut forest, and I've trained the information on the normal data set, created the pipeline, and I tested using the test information. So here I have few fault information. These are fed back to the test after training. This is the outcome of our model. It is effectively able to detect true anomaly and false anomaly using the velocity RMS. Okay. Now I will just show you before going on with the dashboard and alarm mechanism handled. Okay, I'm sorry. I have a dashboard designed here representing all these sensor informations that has been uploaded to AWS. So I've written some SQL queries to extract the table informations and display it as a dashboard in the AWS server. So I'll explain more on this once in the end of the demo. So before going on with the demo, I'll just show you how all three sensors are now communicating with the server, AWS server. So can someone show the video of yeah.
Yes, our maybe you can use our nodes. We have three nodes. Right?
Yeah, so all
This
these
is
three nodes.
our ESP001 node and it's connected to the speaker for the transmission.
And
here's
here's
the
the
second
second
node,
node, which can acquire environmental information.
And here's
Here's
our
our
third
third
node.
node.
It's based
Based
on
on
Arduino
Arduino
and
and
this
this
and it can acquire all of the sensor information, including geometry and acceleration data.
Okay. So here on my screen, so the IoT core is able to get fetch all those MQTT topics. So the MKR is for the Arduino stuff. The ESP1 is from the ESP node. We have two USBs connected, one Arduino connected. So all everything is transmitting the information. So it's getting updated every second. So I have ESP uploading information. ESP2, it's uploading. Yeah, the refresh rate is so slow. So it's now uploading. Now the next place where we are going is here. So now the second place is to check the database. So I'm gonna do a small query. Extracting the stored information. So it's not querying. So it is the tabular information that is being stored in the database. Now this information is now stored. It exists. Now I'm going to extract this in the dashboard. So this is our dashboard demonstrating all those sensor information. We have accelerometer data, gyroscope information, all these sensors attached. Here I'm able to select all three devices. First one is the Arduino. It's transmitting the sensor information. We have gas resistance, indoor air quality, carbon dioxide, temperature, humidity, vibration, information, everything. And with the other two ESPs, so it has the accelerometer data, sending accelerometer, temperature, humidity, and these four sensors doesn't exist for the ESP. So for demonstration purposes, so the ESPs will send the accelerometer data and the humidity temperature information. MKS Arduino is the only sensor containing all the sensor information. It's now transmitting everything. So we have all information gathered here, displayed. So now it is with the machine learning part, how the microservice Lambda has been applied for detecting the fault signal that we are getting so far, if any. Okay, so it's a two block, like we need to add a trigger, and we have the service called simple notification system that will let's email output whenever we have a trigger coming up for the service Lambda. So just to explain, give you a overall outlook on how this code works. Like we have the model train stored in the database, and we are just creating a client for the database streams, time stream. So these are the information for calculating velocity RMS values, integrating it. So we have the time series information. So we are doing a sliding window thing. Since it's a time series, we cannot take the immediate output that we are getting. So we need to take effectively a window information to calculate the velocity, displacement, and all those informations. So we have a lambda handler. It's a micro. It's a parallel function, but it will activated once it sees uh, uh, faulty signals, and once the prediction is fault detection happen, it sends a fault detector notification to the email. So this block is responsible for sending email. So in order to create um, a virtual faulty environment, because the machine learning model is trained on uh, having when the machine has high temperature, high humidity, high gas resistance, poor air quality, and higher, lower velocity and displacement RMS. So for that, to demonstrate, I have a sample example signal pre-programmed within the program. So this replicates the real-time situation, like having poor air quality, higher temperature, very high temperature, very high displacement RMS, very low displacement RMS, very high carbon dioxide in the environment. So with this very, very abruptly showing faulty signal, I'm checking for the cases. I'm defining function for fault detection. So this overall block will detect the input signal in the window that for 1 minute, and finds out whether this signal is faulty or not faulty. But since it is a test case, we have brute forcefully given true fault signal for this program to activate, just to show that the alert system is working right now. I'll give maybe 29. So for the signal detected sent, I got a notification from the Amazon saying all signal detected. It's artificially injected signal representing the real-time scenario of high temperatures, very high, very poor gas readings, very poor air quality. So with this project, we were able to detect our machine learning program could detect the false signals, like to produce the alarm for the engineers. Going back to the cloud infrastructure, okay. And we have the dashboard updating. Yeah. Okay. Thank you, Professor, for giving us the opportunity for demonstrating the predictive maintenance alarm system. So we have demonstrated how signals are fetched, how signal is being processed, what features are effectively required for understanding the fault operations, so we could send an alarm. So I've demonstrated, we have created the machine learning program, trained, tested, tuned for perfectly detecting the fault signals. So our machine learning model is effective of 88% at all times. So it is a good thing because we are just binary classification and without labeling the input signal, whether it is from faulty or normal information. Then to cover up overall thing, our AWS infrastructure is able to detect the fault signal and produce an email alert representing an alarm case, alarm information to the user. So thank you.